Hello everyone, this is Mr. Kalimullah. The topic of my final year project is a network reconfiguration of IEEE standard system 3369 and 119 bus using PSO and genetic algorithms. My supervisor is Engineer Shoaib Ahmed Sheikh and co-supervisor is Engineer Muhammad Fawad Sheikh. This is the outline of my final year project, which includes introduction, motivation, problem statement, literature review, aims and objectives, methodology, results and discussions, conclusions, future recommendations, and then references. So moving towards introduction. An electric power system is a network of electrical components deployed to supply, transfer, and use electric power. Radial distribution system normally consists of main feeders and lateral distributors. It acts as a bridge between high voltage transmission line and the low voltage user ends. When electric power systems are expanded, the losses in the distribution network will increase, which causes a decreases in power factor and voltage profile. Reconfiguration in the distribution system plays a vital role in minimizing the power losses and maximizing our voltage profile. Also, reconfiguration makes a system more reliable. So this is the motivation behind making of our final year project. In existing radial distribution power system, there occurs a significant power losses due to which end users faces a low voltage profile. So in order to overcome these problems, our motivation is to reconfigure existing IEEE standard system 33, 69, and 119 bus, which helps an improvement of voltage profile and minimizes power losses. There are significant advantages of reconfiguration. Some of them are given as to assure our service reliability for more customers during fault conditions and outages. If we tie two radial feeders at this condition, the current in the heavily loaded feeders will be transferred towards the lightly loaded feeders, which results to establish a uniform current along the feeders. And thus, the losses depends on the tie line current and the actual current. By reconfiguration, we can reduce our distribution network losses. Also, it improves our voltage profile. Moreover, it reduces a short circuit current in the lines. So what's the problem statement? The problem statement are about 13% of total power generated is consumed as power losses at the distribution system. A high reactive power flow in radial distribution network, due to which there occurs a low power factor. A low voltages at far end buses in radial distribution network. High power losses in radial distribution network. The low voltages and high current characteristics in radial distribution system leads to a high power losses compared to that of transmission system. We go through a literature review. Some of them are given as in 1975, Merlin and Beck introduces a simple inverter method for calculating the losses through the network reconfiguration. Merlin and Beck first proposed the theory of utilizing existing ties and signalized switches to reconfigure the distribution system for minimizing line losses during a specific load condition. The second one is in 1989, Baron et al. Developed a heuristic algorithm based on the idea of branch exchange for loss minimization and load balancing. This method was time consuming due to the complicated combinations and large scale system. Another one is in 2019, A. Abul Ala et al. Proposed a procedure to seek about the optimal tie switches position and provide the minimum number of signalized switches and the branches to reduce the system losses. In 2007, P.V. Prasad et al. Proposed a distribution system network reconfiguration is an operation that changes the open-close status of signalizing and tie switches to change the topological structure of our distribution feeders. These are the aims and objectives of our project to ensure the optimal tie lines for distribution network reconfiguration on which there occurs optimum voltages profile and minimum power losses. Also, usage and comparison of PSO particle swarm optimization and genetic algorithm for the reconfiguration of IEEE 3369-119 bus system. So, our proposed solution is a reconfiguration, which means to alter the feeder's topological structure by managing the open-closed status of signalizing and tie switches, which is performed in order to reduce the power losses and distribution system and power networks. Our project will focus on finding the optimal tie lines for which voltages profile will improve and decreases the power losses of the distribution network. So this is the methodology. We have used a software, PSSE 34 Power System Simulation for engineering for analysis of IEEE standard bus system, whose logo is given as. Also, we designed and analyzed IEEE 3369 and 119 bus power system and PSSE and algorithm programming and MATLAB software. In each system, a comparison is made among nominal system with a multiple tie lines using a tie lines and the radial distribution system. We have reconfigured the network using three different techniques for analyzing a system thoroughly. These three techniques are hat and trial method, PSO algorithm, genetic algorithm. This is a flowchart of our final year project. We have started with a convergence of IEEE 3369 and 119 bus system. Then we reconfigured the IEEE 3369 and 119 bus system by placement of tie lines. Then we take average value of impedances of lines for tie line impedance. And here we use average value of lines where we use a direct method and indirect method, which will be explained in upcoming slides. Also, we take impedance of lines from cable data for tie lines impedances. Here we use a 3-core aluminum conductor and air at 40 degrees centigrade, which is average temperature of sucker, having current capacity of 0.395 kiloampere, 12.66 kV, 3 by 2 square millimeters. Cable resistance 0.160 and reactance 0.085 ohms per kilometer by using a direct method and indirect method. We have used a direct and indirect method in both cases. Then we performed voltages analysis, short circuit analysis, and power losses. Also, we apply particle swarm optimization and genetic algorithm in both cases. Then at last, we performed cost analysis on proposed tie lines having a low power losses. So that's the final year project flowchart. So this is the base case of IEEE 33 buses system, where the distance between two buses is 1 kilometer, and the tie line is presented by a dotted line where sectionalized switches is presented as. So this is the single line diagram of IEEE 33 buses system, whose average voltages in per unit is 0.945. Power losses in megawatt is 0.21 megawatt, and short circuit current in kiloampere is 1.8314. So this is the direct method where we will be connecting a tie line by using a direct method. So here we have connected a tie line between 8 and 21 buses, which is mentioned as. Now we have connect a tie line from 8 to 21 to base case using a direct method. Here we can see the voltages average per unit increased as 0.9593. Power losses reduces is 0.16 megawatt, where the short circuit current and kiloampere of the buses increased as 2.00 kiloampere. So this is the indirect method where we will be connecting a tie line between 8 to 21 using indirect method. So this is a tie line where we have connected. Here the voltages average and per unit is increased as 0.9547. Power losses in megawatt reduces as 0.18 megawatt, and short circuit kiloampere is 1.9365 and kiloampere. So we have performed a different analysis of buses voltages, short circuit current, power losses analysis by using average value of lines, direct method, buses voltages, short circuit current, power losses analysis by using average value of lines, and direct method. Same, we have performed analysis by using cable data, using direct method, and by using a cable data of lines, using indirect method. So how we select the buses impedances and distances? Here, by using a direct method, we have connected a tie line from 8 to 21. So here we have taken the distance as 1, 2, 3. So here we have taken the distance as 3 kilometer. So here are the calculation for a tie line resistance and reactances. By using indirect method, we have connected a tie line from 8 to 21. Whose distance can be measured as 1, 2, 3, 4, 5, 6, 7, 8, 9 kilometer, and whose calculation are given as. So in this way, we have select the buses impedances and distance. Moving towards results and discussions. There are 3 methods used in our work through which we will be obtaining the results. Those 3 methods are hat and trial method, particle swarm optimization, genetic algorithm. So this is the control analysis of IEEE 33 buses system before reconfiguration. So this is the profile of voltages per unit whose scale can be shown as. Now, this is the control analysis of IEEE 33 buses system, in which we have connected a tie line from 8 to 21 using a direct method average value. Here we can clearly see that the voltages profile is improved, due to which the power losses in the network is reduced. So this is the basic function of reconfiguration. By reconfiguration, we can reduce our power losses in the system, and we increases the voltages profile of the system. So on x-axis, we have a buses numbers for IEEE 33 buses system, and on y-axis we have a buses voltages and per unit. The dotted rated line shows our voltages in per unit of base case, while the others shows the voltages in per unit of tie lines. So here we can clearly see that the voltages profile is improved by using different tie lines one by one in the system. So by reconfiguration, we enhances the voltages profile, which is shown clearly in the following graph. So this is a reconfiguration of IEEE 33 buses system using a different techniques. Here we uses average value of lines direct method. Here we use average value of lines indirect method. And by using a cable data of lines direct method and by using a cable data of lines indirect method. So we have performed a multiple analysis in order to check the buses voltages, the voltages profile of the system. So in case of 33 buses system, this is the comparison of base case and a fruitful proposed tie line. This is the voltages analysis. The orange color graph shows a base case voltages profile of IEEE 33 buses system, and the green one shows a tie line which is connected from 12 to 22 using a direct method average value, while the yellow color graph shows a tie line, a voltages profile in which we connected 12 to 22 tie line using a direct method cable. So here we can clearly see that by using a tie line, we have improved the voltages profile when we compare with base case. So this is the power losses comparison. This is the best case where we have 0.21 megawatt losses. By connecting a tie lines, we have reduces power losses from 0.21 to 0.16 megawatt. And by connecting a tie line from 12 to 22 using direct method cable, we have reduced a system power losses from 0.21 megawatt to 0.15 megawatt. So by connecting multiple tie lines to IEEE 33 buses system, we have analyzed that by connecting a tie line from 12 to bus 22 using a cable data offline and average value offline, by using a direct method, the power losses are reduced about 29% of base case. That's the ultimate which is the ultimate purpose of our final year project in order to reduce the power losses and to enhance the voltages analysis. So this is the IEEE 69 buses system, a base case. So now we will be reconfiguring this network by using multiple techniques in order to connect a tie line in this base case. So here we have reconfigured IEEE 69 buses system using a different techniques. So same, we have performed a multiple analysis. After performing a multiple analysis, we have reached a conclusion. This is the comparison of base case and fruitful proposed tie line. Here we have clearly see that with reference to base case, by connecting a tie line from 5 to 58 using direct method cable, the voltages profile is improved. And the power losses reduces from 0.21 megawatt to 0.09 megawatt. So we can easily analyze from the above depicted graphs by adding a tie line from 5 to 58 using a direct method cable data. Our system power losses decreases and hence voltages profile improved. So here we have reduced almost 60% of power losses of the system. This is the base case single line diagram of IEEE 119 bus system. Now we will be reconfiguring this network. So same, we have reconfigured IEEE 119 bus system using a different techniques. So same, we have performed multiple analysis. After performing a multiple analysis, we have made a comparison of base case and fruitful proposed tie line. This is the voltages profile graph of base case and tie line, which is connecting from 118 to 123 bus using direct method cable. So hence, we have clearly found out here the voltages profile improves and a system power losses reduces from 1.31 megawatt to 1.17 megawatt. We can easily analyze from the above depicted graphs by adding a tie line from 118 to 123 using a direct method cable data. Our power system losses decrease and hence voltages profile improved. So here we have reduced almost 10% of power losses of the system. Also, we have worked on a real-time data. We have done with the reconfiguration of SEPCO region based on NEPRA grid code using PSO, in which we have analyzed that the system losses reduces. Also, the system reliability increases. We have given the data of SEPCO region, which was not for a radial distribution network, but we have implemented NPSC in order to find out whether the system voltages profile improves or not. So here we have clearly seen that the system voltages profile improved and power losses reduces from 14.69 megawatt to 14.66 megawatt. Also, we have used algorithms. We have used a PSO algorithms in order to find out the optimal tie line location. PSO stands for particle swarm optimization. Particle means possible solution to the given problem, and swarm means collection of particles. Optimization, it's a simple action to make the best utilization of resources. PSO helps in computation with hard problems and to solve optimization problems. PSO is population-based algorithms and stochastic algorithms, something which is randomly determined. So it's called a stochastic algorithm. It works on fatness value and it updates population with time passage. So this is the power flow of PSO algorithm. So here we can clearly see that how the system converges on one point. Here the system is converging on 0.15 megawatt losses. And this shown that the system converges on one point, which is the best optimal tie line location on which we have a low power losses. So here we have optimized 33, 69, and 119 bus system using PSO algorithm. So this graph shows the convergence behavior of IEEE 33 bus system, 69, and 119 bus system. We analyzed by using PSO algorithm. We obtained those tie lines in IEEE 33, 69, and 119 bus system on which there occurs minimum power losses with reference to a base case. Also, we have performed a genetic algorithm. Genetic algorithm is more advanced than PSO. Genetic algorithms are stochastic search methods based on natural genetic principle. They try to find out the best solution for the evaluation fitness function of an optimization problem. Genetic algorithm requires less iterations for optimization. So this is the flow chart of genetic algorithm, how the genetic algorithm works in order to find out the optimal solution to a given problem. So here we can clearly see that the system converts from 0.21 megawatt to 0.16 megawatt. So this is the minimum power losses as compared to base case power losses. So how the system converts, this graph clearly shows that the system converts at minimum power losses, which shows the optimal tie line location. So same, we have optimized our 33, 69, and 119 buses system using genetic algorithms. So we have analyzed by using genetic algorithm, we obtained those tie lines in IEEE 33, 69, and 119 buses system on which there occurs a minimum power losses with reference to a base case. We have performed a cost analysis as there occurs a significant reduction in power losses due to reconfiguration. The voltage profile improves. On reconfiguration by connecting a tie lines, there occurs a significant cost. Cost analysis is performed in order to find out the cost on connecting the tie lines. Approximated data of 11 kV towers and conductors, which is received from NTDC, is shown in the given table. So we have performed the cost analysis in case of IEEE 33 buses system, IEEE 69 buses system, and in case of 119 buses system. So a system losses were reduced from 0.21 megawatt to 0.15 megawatt loss. In case of IEEE 33 buses system, on which a total cost occurs on tie lines 82,50,000, which is a huge cost. Also, in case of IEEE 69 buses system, the system power losses reduces from 0.22 megawatt to 0.09 megawatt. And the cost occurs on given as. So this is the total cost on connecting a tie line on which we have reduces a power losses from 0.22 megawatt to 0.09 megawatt. So same, we have performed cost analysis in case of 119 buses system. Future work. In future, we will be using significant algorithms apart from PSO and genetic algorithm. We will place multiple tie lines at a time for reconfiguration of network. Also in future, the code for PSO and genetic algorithm can be smarter, so it will reduces human interaction. Moreover, PSO and genetic algorithms can be identifying the systematic relation between a tie line placement and its cost, so that we prefer our desired and economical placement of tie lines and electric distribution network. So these are the references on which we have go through for the literature review and for the whole concept of reconfiguration of the network. So thank you